Right, so let's start the first tutorial for today. Sara Veneziale is going to tell us about fun varieties and how to use machine learning to classify them.
Yeah, thank you. Again, can people hear me fine? Yeah, I have a lot of nodding. That's amazing. Yeah, so the tutorial for today is kind of two examples about what I was talking about using period sequences and very standard data analysis tools. So I think we've seen quite advanced things this week, and I've learned a lot, which is great. But yeah, today we're doing very basic things and just a bit of Python programming, and I hope everyone can enjoy it. Yeah, at the beginning, mostly because the boards look more fun than they probably are, I kind of want to recap what I was saying so I can write some stuff down. So yeah, so our topic is Fauna varieties. So why do we want to do this? I'm a pure mathematician, so I think I do this because it's fun. If you're a physicist, maybe you do it because Calabi-Yaos can be defined as intersections in fanas. If you're someone else, I'm not sure why you care. But this is kind of a fun problem. It's an open problem, and it's really hard. So fanas, as Al was mentioning a couple of days ago, are kind of the building blocks of algebraic geometry. And the classification has been open since the 1980s. And for smooth things, we know smooth, it's known up to dimension 3. So we know for dimension 1, we know there's only one, which is P1. For dimension 2, there's 10, which are the Delpetzers. For dimension 2, 10. And dimension 3, there's 105. It's quite fun. Okay. And dimension 4 is unknown. And probably there's a lot. And higher, it's even more unknown. And if I'm not assuming smooth anymore, it's even more complicated. So we have this new approach that comes from Coates, Corti, Galkin, and Kasparitz, using mirror symmetry to classify fanas. And the whole idea is that we have a one-to-one correspondence, which is conjectured between, on one side, we have fanas up to deformation, which is the correct class of transformation in algebraic geometry. So, and on the other side, we're going to have Laurent polynomials up to mutations. I'm not actually going to explain what either of these things are, but I'm just saying that there is a set with some sort of equivalence relation on both sides, and these equivalence relations are the correct things to do. And the conjecture is that these are in one-to-one correspondence. And the way that they are into one-to-one correspondence is using this mirror symmetry, hard to define thing called the quantum period. So on one side, I'm going to have a fana, X, and I can define something called its regularized quantum period, which is just a series. So it's going to be 1 plus Cm e to the m, m greater or equal than 2. And on the other side of the mirror, I'm going to have a Laurent polynomial, which is called f. And from this, I can define its classical period, which is something, again, similar. And the idea is that X and F will be mirrors of each other if these two power series that I'm computing in wildly different ways are actually the same. And the conjecture is that this very hard to compute quantum period kind of should be a complete invariant of the fanas, so it should have all the information. So in this tutorial, we're going to see very easily how in a specific class of fanas, it contains the dimension as one of the information. Okay, so why do we think that this is a good data analysis kind of problem? Well, first of all is these series are infinite, so we have an abundance of data, so that's great. The fanas, there are a lot of them, so we have an abundance of data there as well. And also, I think something that Al didn't mention is that actually I have an infinite series, right? But I'm gonna chop it at some point and feed it into my computer. Why is that something that I'm allowed to do? Well, actually, these series have a differential operator that sends them to zero. So in this case, there exists L such that L, and this relationship is equivalent to a recurrence relationship on the coefficients. So really, I only need a finite amount of coefficients before I know the whole behavior of the period sequence, which is the sequence of the coefficients. So it is sensible to calculate a certain amount of terms, chop them up, and then do data analysis on this. And the results that we're going to get are going to be representative of the whole sequence. We're not kind of like ignoring and losing information later on because there's some kind of recurrent relation. I should mention though that this is really hard. Yeah, they're very hard to find. They're called Picard-Fuchs operators, and they're not like straightforward, but they exist, so they kind of justify what we're doing. Yeah, of course. I don't know. People that do know are not sure of like, there's not like a formula of like, oh, if my period sequence looks like this, it will be truncated like that. But experimentally, it's been like a few hundreds, and that's fine. So there's no proof or actual criterion. But in our cases, in the data that I'm going to share, I think we compute up to 100,000. So we are like very comfortable that we should be past that point. So we're comfortable in doing what we're doing. Yeah, but there's no criterion, which is sad. Cool. Yeah, if you do have questions, just shout. That's fine. Amazing. So this was the kind of recap what Al said, more or less. And I'm going to recall what the data that we're going to looks like. So we've heard this morning about toric varieties. So not all toric varieties are Fano. Some toric varieties are Fano. I'm not actually going to define them, but the way that I look at toric varieties are as quotients. So I think of toric varieties as having some Cn, and I take the geometric quotient by an action of a torus. The double bar mean that I'm taking this quotient when it kind of makes sense. So this action might not mean that every orbit is kind of sensible. So I do, the actual quotient is going to be something like Cn minus a union of linear subspaces. And in our case, this is the kind of general case where R is going to be my Picard rank of my toric variety. We're going to do the very easy case, which is Picard rank 1, which means that this just becomes a C star. So our interest is in weighted projective spaces. Or whoops for shirts. And what do these look like? We've seen, I think, the definition of projective space a few times in this week. So in my head, these are C n plus 1 minus 0. So in the case of weighted projective spaces, this kind of like extra junk I have to throw away is just the origin. So that's nice. Kind of don't have to do anything else. And it's going to be modded out by an action of C star. And the action is going to be weighted. So how is the action defined? T times Z0 Zn. It's going to be something like T A0 Z0 T A N Zn. And these A0 An are my weights. So this is called the weighted projective space A0 An. And these are weights. Why do we care about these? Well, they're nice and they're easy. And the very hard period sequence I wrote somewhere else, and I said, oh, this is very hard to compute. it has Gromov-Witten theory. Actually, in this case, has a very nice formula. So my coefficient, did I call them C? Yes. My coefficient C ends up there. In this case, are just C K times A, KA factorial divided by the product AAI factorial, where A is the sum. So we notice immediately that this sequence will have a lot of zeros, and you're going to notice it in the data that you can import that if A is very big, then even if I go up to 100,000, then I only will have a bunch of terms. So that's why we go so deep in the period sequence, because A in this case is called the Fano index of the variety, and that kind of determines our pattern of zero within the sequence. So we kind of have to go really deep in order to have enough data to get an idea of what's going on. Amazing. Great. Okay, so I wanted to now just kind of talk you through what we're gonna do. Again, not much machine learning, mostly data analysis, but so what we're gonna do is by applying PCA, you should be able to see that this sequence of integers is kind of two-dimensional, and that comes from the fact that the logarithm of the period sequence kind of grows linearly, so we kind of expect it to be eventually just regulated by two coefficients. And after you've done that, you can just plot it and notice that they're very nice divisible clusters. So this doesn't require us to actually do anything, but for fun, we can fit an SVM and show how we can find some like linear bounds between them. And this is, yeah, kind of two examples of the idea that Al talked about. And just so then I sound like I've talked about theory for a little bit, I just wanted to define and like recall what PCA and SVM is in case someone hasn't seen them. But again, compared to the stuff that we've seen this week is much more elementary. So what we're gonna do, so PCA is principal component analysis, and it kind of transforms data into looking at the kind of heaviest directions. So you're given like the data which has n features. So if you have your data set is kind of tabular, it has n features. And then what do? You compute the covariance matrix. The matrix where the I and j entry is just the covariance of the variable I and j. And then you calculate the eigenvectors and eigenvalues. E vectors, E values. Since the covariance matrix is a symmetric semi-definite matrix, the E values are going to be all non-negative. So there is a concept of like the one that is going to be the heaviest, and that's going to correspond to our first principal component. So you rank the eigenvalues according to the biggest to the smallest, and that way you also rank the eigenvectors, and then you can decide, okay, I want to apply PCA and get the two first principal components. So then you just take your data and you multiply it by the matrix of the eigenvectors, as many as you want, and that will give you your data transformed according to kind of like the heaviest direction of your data. Yeah, we are actually not gonna implement PCA. You're very welcome to try, but we're gonna use sklearn. Kind of does it all for you, which is very nice. Yeah, it's a nice library if you want to do kind of quick exploration of data. And okay, this is how we switch to the other board. Amazing. And then the SVM, on the other hand, is one of the most elementary classification kind of machine learning thing that you can do. So support vector machine, it kind of looks at data in your space, and it tries to divide clusters by plotting hyperplanes. So in our case, you will have something like, these are my class 0, and these are my class something else. The SVM will plot an hyperplane. In this case, it's a line. And then it will see, it will try to optimize the margins from the line to the closest points, or a number of support vectors that you kind of decide. And this is all kind of can be chosen. And by doing so, it kind of finds the optimal kind of hyperplane that separates your clusters. So this is the thing that we're going to do by just linear SVM. Just means that we are plotting hyperplanes. There's different kernels, which means you plot different curves. Cool. I think this is all I wanted to say and bore you about. So on the website in materials, there's a Jupyter notebook that has a kind of sketched out, for example, what we can do. So it asks you to do a bit of data generation of defining what the period sequence is and play around with it and kind of appreciate how, if we go for bigger boundaries of how many data points we want, it kind of becomes very long. So the data generation was actually done on the HPC. And then he asked you to, to do a linear fit, and then to download the data from my Dropbox, which should work. It takes a little bit. And then to import it, which also takes a little bit. And then, just do very standard PCA and SVM and play around with the data. If you have problems, shout. And I think at the end, we'll just go through it together. Questions? Hello. Hi. There's not much. Hey, I just was asked a question and maybe I was being unclear. I think you're asked to log the coefficients. I just mean apply the logarithm to the coefficients, not just some kind of logging function that you might be able to Google. So I'm asking to plot K times A, plot against the natural logarithm of CK times A. Just applying the log, in case that wasn't clear. Okay, so I think I underestimated how long this is going to take, so I apologize for that. But there's 8 minutes left, so I just wanted to go through what the output should look like. And of course, you're welcome to keep working on it or ask me questions about it. So first of all, I apologize for the first exercise. I think I, as I mentioned before, normally run these things with a Sage environment going on, and that deals very well with large integers, and Python deals very badly with large integers. But I think we kind of get a taste of how generating your own data can be really fiddly and annoying. So I think the last speaker today says something about use data that is already available. That's very fair. So we wanted to write a function that tells me the period sequence of a weighted projective space. I wrote logarithm here where I shouldn't have, so it computes the period sequence. And so I have to calculate the sum of my weights. I kind of want to store them in a dictionary where K will be equal to the K in this formula here, but I want to get to upper bound of N, which is going to be something K times A. So I need to range from 1 to the ceiling of an A. And then I do the calculation for the denominator and then just put in the formula, integer division is your friend. And as we all kind of got these kind of are very, very big numbers and they look very horrible. And if we do too many of them, then your computer crashes. So good thing that we're doing this on an HPC and not on our own laptops. And then we were asked to plot the indices against the log periods. So we just had to apply mathlog to every coefficient and then apply just a simple linear regression, because I kind of, spoiler alert, this kind of looks linear. Isn't properly, but kind of looks linear. So this is what it looks like. And my score is very, very good because it's a really good fit. In different ranks of toric varieties, you kind of have more of a period up and down, but for weighted projective spaces, it really looks linear. Okay, then there was a downloading data that I supplied. The data had the shape of like having the weights of each weighted projective space, the indices, which my x values of my of what my coefficients, non-zero coefficients are, and then we'll have the log periods. We're not storing the actual periods because they are humongous integers, so we're storing the logs and chopping them out as floats. I have got it before, and then it was asked to label the data. And this uses the fact that the dimension of a weighted projective space is n, where n plus 1 is the number of the weights. So this just adds another key to my dictionaries, and then kind of printing out how many we have. So we have basically don't have any in the first 3 dimensions, and then it kind of explodes. And this is part of a bigger data set, and I chopped out the bigger dimensions because then it was too heavy to put on Dropbox. But yeah, the smaller ones are small for a reason. Yeah, just one is because there's only one in one dimension. 2 is because there's only one smooth weighted projective space in 2 dimension, and in 2 dimension, like terminal, which is like the type of singularity that we want, is the same as smooth. Then 3 is very small. Anyhow, so the total was 56,000 more or less data points. So then we wanted to do some dimensionality reduction with PCA. The problem is because I have a lot of 0 elements, I've chopped all my period sequence up to, I think, 100,000 here, but different A's will give me a different pattern of 0. So then I have different non-zero elements, which means that my log periods have different lengths. So we kind of like define a minimum very abruptly and then chop all of them according to the minimum. And then we want to do PCA on it with 2 components. So in order to fit it to the PCA, we need to extract the log periods and put them as MP arrays. And then we fit the PCA, well, we define the PCA with 2 components from sklearn, and then we fit transform onto the data, and then we print the exponents various ratio, which I didn't say what it was, but it's the ratio of the eigenvalue by the sum of the eigenvalues. So in this case, we've ordered the eigenvalues so they're like biggest to smallest, and it's saying that the first principal component basically is the most important one, and the second one, very little. So then we can plot the 2 PCA components. So we extract PCA1 and PCA2, and we color by dimension. And we get potentially this scatter plot. I think Al mentioned hedgehogs. You can't really see them here. You have to see them in like better graphs, but like you kind of see the like little mouth, and then it goes up. Yeah, so the smooth people in each class will be at the pointy bit, and then the others kind of change by singularity, and this is how they look. So it's clearly like a linear SVM should do a very good job, and it does. So now we want to fit an SVM with a linear kernel. So we ignore dimension 1 and 2 because we only have one example. So there's not really a way of putting something in the training set and in the testing set at the same time. So we kind of ignore them. So we're chopping by dimension greater or equal than 3. And then we are shuffling our data using shuffle. And then we're doing train test split with the 70% of testing. I know this is a bit silly because I can draw the lines with my pencil, but for the sake of it. Then again, we scale using standard scaler. We fit on the training set and transform both training and testing, define an SVM with linear kernel, and then we can fit. And then if we do the prediction on the testing set and we do the accuracy score, we get, of course, 100% because it's clearly linearly separable. And then we can plot the linear boundaries. And so yeah, I said decision boundaries, but I just meant plotting the lines that divide things. And they come from just the coefficients and the intercepts of the different linear boundaries. Because I have 10 classes, well, now 2 less, I have 8 classes, I will have a lot of decision boundaries, but I ask you to plot only the ones that separate neighboring classes. Then the final graph looks something like this with these really nice lines. Yes, and I think this is all I had to say. Thank you so much for being here.